You've likely heard of Einstein, Darwin, Curie, Newton, and so on, but I bet at least one of the scientists on this list is new, and I think it's about time we heard about them. Let's do it. The bad thing about donating blood is that I always get asked, whose is this and where did you get it from? But the good news is it saves lives, so honestly they should be so picky. Our first scientists developed methods for storing and transporting blood on a large scale. Before this, blood transfusions were incredibly dependent on local sources because they could only be stored for a few days. Charles Drew developed techniques for separating blood plasma from the blood cells. It was then dehydrated to increase storage times and could then be rehydrated whenever it was needed. Because of this incredibly successful technique, Drew was asked to head up the Blood for Britain program, which got donated blood from American citizens and shipped them overseas to the United Kingdom where it could be used for soldiers fighting in World War II. It was during this time that Drew developed the concept we now know as bloodmobile, vehicles with refrigeration so they could be used to transport the blood. In addition to his achievements in medicine, he was a passionate campaigner against the segregation of blood and against the exclusion of black surgeons from the American Medical Association and other medical societies. In 1944, Otto Hahn won the Nobel Prize for his discovery of nuclear fission. That's the process by which nuclear bombs and nuclear power stations produce energy. And while Hahn was the sole recipient of this prize, another colleague, Fritz Strassmann, was given credit as a contributor. But there was another contributor, one who had worked with him for decades discovering new elements, Lise Meitner. Austrian-born Lise Meitner entered academia at a time where women weren't often allowed to be academics. She worked at the Friedrich Wilhelm University with Hahn, both of them taking unpaid roles in order to be able to carry out the research that they wanted to do. The work that she is now at least most recognised for is working out the mechanism by which a neutron can collide with a uranium nucleus, splitting it up into fragments. And this is the process by which nuclear fission works, both in power stations and atomic bombs. Hahn had carried out an experiment and figured out that one of the products was barium, but he didn't understand how it could be possible. Without Meitner's calculations, he never would have been able to publish his results and subsequently never would have won the Nobel Prize. Despite being nominated by her colleagues for either the Nobel Prize in Chemistry or the Nobel Prize in Physics 49 times, Lise Meitner never won. She was invited to join the Manhattan Project developing the atomic bomb, but she had an ardent dislike of weapons and wanted nothing to do with it. Among the influential and famous scientists of the time, she was well known and respected, with Albert Einstein referring to as the German Marie Curie, despite her not being German. But it was only after she died in 1968 that her name began to circulate outside of that small and intimate group. When you studied the behaviour of light at school, you probably saw some diagrams that looked a little bit like these. These show how light travels in straight lines from a source. If you wanted to see something, then the light has to make its way from that source, reflect off it, and then go into your eyes where your brain can process the information. This is often taught as fact, but rarely is it attributed to its discoverer, Ibn al-Haytham. Al-Haytham was born in Basra approximately 1,000 years ago. He did extensive experiments with light and was very curious about how light worked and how it was interpreted by humans. His most famous work, the Book of Optics, was translated into Latin and was hugely influential around Europe, challenging the established idea that our eyes produce light rays that helped us detect the world around us. Al-Haytham suggested that our eyes receive light from objects, both luminous and non-luminous, and was the first to suggest that vision occurs in the brain. He also utilised the pinhole camera, or camera obscura, to prove his ideas about how light is transmitted, and also used this to show that the moon was a crescent shape when experiencing a solar eclipse. He also pioneered the scientific method, utilising it in all his experiments some 500 years before Renaissance scientists in Europe. He also wrote extensively on philosophy, theology, medicine, maths and astronomy. What a guy! When Julius Caesar was 30 years old, he allegedly encountered a statue of Alexander the Great. Realising that Alexander had died at the same age that Caesar was now, and had accomplished huge things. He was undefeated in battle and had conquered massive swathes of land across Eastern Europe and Asia. Caesar had accomplished comparatively very little, so much so that he fell to his knees and wept. Our next scientist accomplished some amazing things with significantly less death and destruction, all before her death at only age 24. If there was a statue to her, I think a lot of scientists would do as Caesar did. But before we can talk about her, we need to talk about Hawaii, specifically the island of Molokai.
Live from Hawaii's beautiful Molokai Island. We're not just for lepers anymore.
In early 20th century America, if you suffered from leprosy, a bacterial disease affecting the eyes, skin, nerves, and a whole bunch of other parts of your body, you'd likely be sent for treatment in Hawaii, usually Molokai. In theory, it was to give you a chance to rest and recuperate, but mostly it was to send you somewhere pleasant and warm to die. Treatments did exist, and for hundreds of years, one of the most effective was something called Cholmugra oil. The issue with it was that it was very sticky, it tasted bad, and had exceptionally high viscosity. You could inject it under the skin, but it would cause the skin to blister up and scar. Enter Alice Augusta Ball. At age 23, having graduated from the University of Washington, having a paper published in the Journal of American Chemical Society, receiving a master's degree from the College of Hawaii, becoming the first woman and first black American to do so, she solved the problem of using Cholmugra oil. Ball developed techniques for separating certain chemical components of the oils, reducing the viscosity and allowing it to be absorbed by the skin, without losing the properties that made it such an effective treatment for leprosy. Apparently some 78 people when given this treatment were sent home from Molokai. But before Ball was able to publish her results properly, she fell ill and died at age 24. Luckily, her graduate study advisor and dean of the university, Arthur Dean, I guess he was Dean, he found her notes and was able to work out how she had developed the technique. Unluckily, he decided to take credit for it himself. Even went so far as to call it the Dean method and failed to give Ball any credit whatsoever for this technique. What a little In a pleasant act of retribution, one of Ball's colleagues, Harry Holman, published a paper a few years later referring to it as the Ball method and contesting that Dean had had any significant changes to the technique that would allow him to claim it as his own. Still, it took until the year 2000 before Ball received anywhere near the recognition that she deserved. Her technique remained the premier treatment for leprosy until the development of certain drugs in the 1940s. Electrons are negatively charged particles, without which you couldn't be watching this video. Atoms have a nucleus which is positively charged overall, because it's got positively charged protons and neutral neutrons. So how can a positively charged nucleus spit out a negatively charged electron? The answer is beta decay. In order to explain beta decay, you think of a small neutral country like Switzerland. And imagine Switzerland decided to get all of their negative and gloomy people and just fire them out of a cannon. All that would be left behind is the positive, happy people. Switzerland had gone from neutral to positive by getting rid of all of its negativity. Okay, I'm editing the video now and I realised that I made a mistake. We already know Switzerland is positive because of the flag. Now, that's not what we mean when we say Switzerland is neutral, but in particle physics, a neutrally charged neutron can eject out a negatively charged electron and leave behind a positively charged proton. Yeah, particle physics is weird. And Xiansung Wu understood it really, really well. She worked on a variety of different experiments showing particular affinity for elements of neutron absorption. Yes, the same method that Lisa Meitner developed a mechanism for. She contributed to the Manhattan Project by improving methods that are used to separate out uranium isotopes and finding ways to develop enriched uranium fuel, and expanding on beta decay to prove the theory that was originally put forward by Enrico Fermi. And finally, in her big famous experiment, Wu proved that parity is not conserved for beta decay. Now, what the hell is parity? Parity is the idea that if there was a world where left and right were swapped, kind of like in a mirror, it wouldn't make any difference because all of the physics properties would remain exactly the same. If I throw this fruit up in the air, mirror me does the same thing, and the fruit rises and falls at exactly the same rate, showing that the same physical properties are obeyed. However, if I spin my finger around, then mirror me isn't making the same movements. In order for me to match that movement, I'd have to use my left hand, and then mirror me's using the right hand, and the whole thing is not the same at all. This is a very basic analogy that can just help us understand the complex nature of parity. Now, the Wu experiment, as it's known now, was the result of a suggestion by two theoretical physicists, Sungdao Li and Chen-Ning Yang, who approached Wu to see if she could carry out an experiment for them. And she carried out the experiment, and she proved that parity was not conserved for beta decay, something which profoundly shook particle physicists at the time. It was such a big deal that it helped influence the development of the standard model of particle physics, a theory which can explain 3 out of the 4 fundamental forces in the universe. Only missing out, pesky gravity. Li and Yang won the Nobel Prize for this prediction, confirmed by Wu. And despite their efforts to have Wu included and the astonishment of the scientific community, Wu was repeatedly turned down for the Nobel Prize herself. While she did eventually win the Wolf Prize, which is awarded to people who should have had a Nobel Prize, her later years were full of activism for gender equality in the science community, something that's still been fought for this day. It's kind of tragic how Lisa Meitner was not awarded the Nobel Prize because her work was too theoretical, and Xiansung Wu was not awarded the Nobel Prize because her work was too experimental. Weird how that happened to 2 women. But hopefully we've been able to shed a light on some scientists who you may not have heard of, and whose contributions to science and the world in general made it a better, more interesting place. Now, these scientists made massive contributions by being right, but if you're curious about what happens when scientists are wrong, then you should watch this video next.